Now what we're going to do is we're going to talk about the motor principle, and of course what we're talking about here is nothing more than a look at what happens when we have two different magnetic fields interacting with each other. Okay? So what I want you to do is really quickly take a look at the far left of this diagram, and you'll notice that we've set up here an external magnetic field. What we have here is the north pole of a permanent magnet located at the top, and the south end of a bar magnet located at the bottom. Now, by convention, what we're going to do is we're actually going to draw a magnetic field between the north and the south pole. Okay? We know for a fact that between the north and the south pole of a magnet, normally there is this force of attraction between the two, but there is also a magnetic field that exists between the two. Magnetic field lines are always drawn from north to south. So let's start off by doing that. If I draw magnetic field lines going from the north pole of a bar magnet to the south pole of a bar magnet or of a permanent magnet, you would see magnetic field lines that look like this, going from north to south. I don't know if you remember this or not, but there is a symbol that we often use for magnetic field lines. And that symbol that we use is nothing more than a capital B. Now, whenever we have bar magnets or permanent magnets creating a magnetic field, we often refer to these magnetic field lines as external field lines. So what we'll do is we'll denote the magnetic field B with a subscript EXT that represents external. Now, if you take a look just to the right of that, you have once again a wire, and there's a cross that goes right through that wire, which represents current flowing through the wire so that it's going towards the screen and away from you. So if you recall, think back to right-hand rule number 1 for straight conductors. Here's a straight conductor with current going away from you and towards the screen. What you're going to do is you're going to wrap your right hand around that wire so that your thumb is going in the direction of conventional current flow, which means that your thumb should be pointing towards the screen. And if you wrap your hand around this wire, you'll notice that your fingers tend to wrap around it in a clockwise direction. So what would that look like? Well, if I had to draw that clockwise magnetic field, it may look something like this. Okay, I'll just draw several of these. I'm not going to draw too many. I don't want the diagram to get too complicated. Okay? So those are the magnetic field lines that exist around that straight conductor. Now again, because this is a magnetic field, I will denote this with a capital B that tells me that it is a magnetic field. But these magnetic field lines are not external magnetic field lines. These are actually induced magnetic field lines, which means that they are brought upon by nothing more than the current that flows through the wire. And because it is an induced magnetic field, I will put down a subscript IND to represent induced magnetic field. Okay? Now, here's where things get really, I guess, tricky, if you will. What I'm going to do here is I'm going to take my induced magnetic field, and if I bring it into my external magnetic field, you'll notice that two things tend to happen. Okay? First of all, you'll notice that if I look directly to the right side, and again, I know it's going to be a little difficult to see here, but if you take a look on the right side that I've circled here in black, you'll notice that the external magnetic field lines, which I've colored in blue, and the induced magnetic field lines, which I've colored in red, they all tend to go in the same direction. In this case, towards the south pole. On the other hand, if I take a look directly to the left side, you'll notice that the external magnetic field lines do go south or towards the south pole, but if you look at the induced magnetic field lines, the ones that you see in red, they're actually going in the opposite direction, towards the north. Okay? And to show this a little better, what I've done here is on the far right side of this handout, you'll notice that in a much cleaner version, you see something that looks like that. Now, in real life, what actually happens is that the magnetic field lines happen to interact. And when they do interact, what happens is you get a magnetic field line diagram that looks something like this instead. Okay, and you'll notice that for some reason it's almost as if there's some kind of a wave-like a wave-like push that happens. So that again, if you take a look at the far right side of the wire, the magnetic field lines tend to be very dense. Whereas if I look at the left side of the wire, magnetic field lines are not so dense. Okay, and one of the ways I sort of try and describe this is by saying that if I look at the right side of the wire, the magnetic field lines are all going in the same direction, which means that what you have here is a much stronger magnetic field. Okay, so let's just write down that we have magnetic field lines stronger. Okay, in fact, not only are the magnetic field lines stronger, but you can see that they happen to be in higher density. Okay, or you'll notice that there's a higher concentration of magnetic field lines on the right side. So I'm going to write down that the magnetic field lines are stronger and that we have a higher concentration of them on the right side of the wire. If you take a look, on the other hand, at the left side of that wire, it turns out that the induced magnetic field and again the external magnetic field, as we said before, are going in the opposite direction. So it's almost as if the two magnetic field lines are kind of canceling each other out. Now, they don't really cancel each other out because, of course, one of the magnetic field lines isn't directly, they're not going in straight lines. One of them is circular, of course. What we're going to say here is that the magnetic field lines on the left tend to be a little bit weaker. Okay? And not only are they weaker, but there tends to be a lower concentration of magnetic field lines on the left side of that wire. Now, what happens is this, and one of the things I like to do here in this case is I like to use an analogy from biology. I don't know if you remember learning about something called osmosis or maybe the diffusion of particles, but generally speaking, things like to move from areas of high pressure or high concentration to areas of low pressure or low concentration. In this case, the lower concentration or the lower pressure area happens to be the left side of the wire. And for that reason, something happens to the wire itself. The wire actually ends up moving towards the left. In other words, it's pretty much what we're trying to say here is that there's actually a force brought upon by the magnetic field on the wire. And that force is often called the magnetic force. Okay? So that wire physically moves to the left. Now, how do you sort of explain this? How do you, what exactly are you talking about when I talk about right-hand rule number 3? Well, right-hand rule number 3 is very simple, but in this case, what you're going to do with your right hand is you're not going to form you're not going to form a curl with your fingers. This time, what I want you to do is I want you to take your right hand with your fingers straight, so you're an open hand. I want your fingers, your thumb, and your palm to be all perpendicular to each other, kind of like this diagram over here. If you look at this diagram over here, you'll notice that on the right hand, the fingers represent the direction of the external magnetic field. The thumb represents the direction of conventional current flowing through the wire. And of course, the palm represents the direction in which the magnetic force is going to be applied. Kind of makes sense because whenever you push something, usually you use your palm to push an object in that particular direction. So what we're going to do here is we're going to do a few examples for you, okay? And hopefully you'll understand how right-hand rule number 3 or the right-hand palm rule tends to work. Here's some sample problems I want you to have a look at. So in diagram number 1A, which is this one over here, I want you to take a look at the two permanent magnets. We have a south and a north. So as we said before, what we're going to do is we're going to start off by drawing the external magnetic field lines. You know for a fact that external magnetic field lines always go from north to south. From north to south. Okay. So here's what I'd like you to do to start off with. With your open right hand, I want you to use your fingers and point your fingers toward the left. If you point your fingers towards the left, okay, your thumb now, you'll notice that the current in the wire is going out of the page towards you, which means that your thumb should be pointing directly at you. So once again, your open hand fingers to the left, and your thumb is pointing directly towards you. If you do this properly, you'll notice that your palm is actually facing down. What that basically means is that this wire, something happens to it. It turns out that there is a force, a magnetic force, that acts down on the wire. And guess what that wire starts to do? It actually moves down in the direction as shown by the magnetic force. Take a look at diagram number 1B. Okay? Now this time, what we have is a wire with current going towards the left. So if you take a look at the cross section of the wire, there's a dot there, and that dot basically means that current is going in this direction. Now, if you look at diagram 1B, you'll notice that there's a whole bunch of these little X's here as well. Guess what those X's represent? Well, in this case, X's always, again, represent things going away from you. Okay? So these X's, in this particular example, they actually represent the external magnetic field. So the external magnetic field, and you have to kind of think three-dimensionally here, is actually going towards the screen and away from you. So here's what I would like you to do. With your open right hand, I want you to point your fingers away from you and towards the screen. So if you point your fingers towards the screen, okay, now what I want you to do is take your thumb and make sure that your thumb is pointing in the direction of current flowing through the wire, which in this case is to the left. So if you point your thumb to the left, you'll notice that now, once again, your palm is facing down. So if your palm is facing down, well, guess what that means? This wire will now have a magnetic force acting on it in the down direction. What does that mean? That wire will accelerate down. Okay? Hopefully that will clarify a few things for you. Now, before I actually finish the session, I'll do sort of a different type of question for you. If you take a look at this next diagram, now I know it says 1A again. It's actually not number 1A. It's really 2A. Number 2A. We're looking at this diagram over here. Now, in this case, I've given you different pieces of information. Now, I don't know if you can see this or not, but in this particular diagram, I've actually given you the direction of the magnetic force, and I've also given you something else. I've also given you, I don't know if you can see these little dots here, but these dots represent the direction of the external magnetic field. And what I'm asking you to do in this case is tell me what is the direction of the current flowing through the wire. Okay? Now, if you take a look at the external magnetic field, you'll notice that the external magnetic field lines, well, because they're represented by dots, that means that the external magnetic field lines are going towards you. So away from the screen and towards you. Now, I know it's going to be a little bit weird or a little difficult to do. What I want you to do is with your open right hand, point your fingers towards you. I know it's a little bit tricky. I know unless you're very flexible, it's going to be tough to do, but point your fingers towards you. If you look at the direction of the magnetic force, it's towards the left. So somehow now, what I want you to do is I want you to point your palm. The palm of your right hand should be pointed towards the left. So if you do this properly, once again, your open fingers towards you, your palm towards the left, and if it's done properly, you'll notice that your thumb is now pointing directly down. Okay? So if your thumb is pointing down, that means that the direction of the current flowing through the wire must be down. So if I go up to where the cross section of the wire is, which is at the top of the wire, you'll notice that there's a blank there. Okay? That means current goes from the top towards the bottom. To show this, I put a cross, okay, where that cross section is to represent current going away from the top and towards the bottom. Okay, I'm going to end this session here, so hopefully that helps you out. Stay tuned. We're going to start talking about electromagnetic induction in the next period. Thank you.